Hi, everyone. Welcome to Riot's Lunch and Learn series. My name is Caroline Griffin. I am Riot's Director of Operations, and I am super excited to have Rob Lauer, Developer Relations Lead at Blues Wireless, here today to talk about building a portable speed trap with TinyML and Raspberry Pi. Just a couple quick reminders before we get started. This is being recorded. It will be posted to Riot's YouTube channel and will be shared via the meetup group where you registered for this event. And if you have any questions throughout the event, please do place those in the chat box. We will give you an opportunity to have those answered and even unmute yourself at the end and have Rob interact with you. But without further ado, I know you're all here to hear from Rob, so I'll hand it over to him. Thanks for being with us, Rob.
Awesome. Thank you, Caroline. Hi, everyone. Thanks for having me here today. Welcome to this little lunch and learn as we cover, a pretty silly slash useful slash pragmatic topic, and that being machine learning on the Raspberry Pi. But of course, it's through the lens of a kind of ridiculous but still fun project, that building a portable speed trap. So I'm going to be cramming a lot of topics and concepts into our time today, including the ones you see here. I certainly don't mean to talk down to any of you, as I'm sure many of you know a lot more about these individual topics than I do. But I do say this because I don't like to assume too much knowledge, right? I like to, I don't know, assume my audience is kind of like me, sort of a beginner slash intermediate slash has raging imposter syndrome from time to time. So just so you know, that's kind of the perspective I'm taking here. Again, quick intro. My name is Rob Lauer. I'm Developer Relations Lead at Blues Wireless. If you're a Twitter person, you can find me there at Rob Lauer. And yes, I work for this company called Blues Wireless. No, we are not the guys selling burner phones at your neighborhood mall, but rather an IoT company that's really here to make cellular connectivity easier for developers. And what do I mean by that? Well, at Blues, our core mission really is to make cellular IoT easy for developers and affordable for all. And I promise this is completely relevant to what we're talking about today. Our focus really is on securing your data from the moment it's acquired by a sensor all the way through to landing on your cloud app of choice. All of our hardware solutions are low power out of the box to the tune of about 8 microamps when idle. We're also very much a developer focused company. Most of us at Blues here are current or former engineers. So, we know the pains that you all experience, and we're really building solutions to ease those IoT connectivity burdens. And I know this all kind of comes off as a little bit salesy, but I do want to run briefly through our products a little bit here. It could kind of help visualize where Blues Wireless fits into a given IoT solution. So we start with our sensors. You're acquiring data of all types, from temperature to humidity to motion or gases, whatever it may be. This data is, of course, likely processed by a microcontroller or single board computer, but you need to get that data to your cloud. So you'd then be using the Blues Wireless Notecard to securely deliver data over cellular to your cloud, to our cloud service, Notehub, which then lets you securely route data to your cloud of choice. So with Notecard and Notehub, we're taking a lot of pain out of that kind of secure transfer of data and conforming to whatever data structures your remote endpoint is anticipating. And everything with Notecard and Notehub, as you will see today, is accessible via developer-friendly JSON-based API. So everything is JSON in and JSON out. All right, so now let's set the stage for this project a bit. So my story really began a while ago. As part of the pandemic, for me and my family, meant filling this, newfound time void with, frankly, just like walking around the neighborhood. And I started to notice that certain roads really get a lot of traffic, and people are clearly, to me, from my opinion, like speeding through them at a bit of a ridiculous rate. So I decided to kind of prove my point out, and I wanted to stop kind of assuming what I saw as some relatively reckless driving behavior and start proving it out. So of course I thought, being the kind of person I am, I thought with the right hardware and the services, I probably could build an IoT project that would do just that. And this of course became what I've termed a portable speed trap. Okay, so I start thinking about how I'm going to build this project. I knew I would need a powerful microcontroller, probably, or just a single board computer like a Raspberry Pi. But from there, I knew I'd be using something called machine learning, which I barely understood. I'd need a camera to take video samples, language like Python to program some logic. Then there's the issue of running it off the power grid. And what about data connectivity outside of Wi-Fi? much less relaying that data to a cloud-based dashboard. And, then I got myself in a tizzy right away. So I went ahead, like most of us do, and maybe create a little to-do list. And frankly, that didn't make me feel much better. Now I've got, 7, 8 tasks here that I need to solve. Everything from finding the right hardware to writing firmware or Python scripts. We've all pretty much been here. But then, yes, I channeled my internal Bob Ross and took a deep breath. And none of these problems are, of course, unsolvable. And for me, I kind of needed to start at the beginning. And so the first real step for me, at least, was to answer this question: what is machine learning actually? I knew I needed to use, or at least wanted to use, some form of ML for this project. But I'll be honest, that's kind of all I knew at that time. And if I knew anything about machine learning before starting, it's that 60% of the time it works every time, right? It's highly imperfect. Case in point, as an engineer, my instinct wasn't to read any silly guides or tutorials. It was frankly just to download some code and start using it. And literally one of my first attempts at an ML concept called image classification was taking a little squishy stress ball thing and running it through an available, like a pretty popular image classification model. And, the results were sketchy at best, which I kind of anticipated, but it was, humorous to see at the very least. So I knew I would have to do a little bit of research. And so I really started my ML journey by reading quotes like this. So ML is the study of computer algorithms that improve automatically through experience and by the use of data. It's seen as a part of AI. Okay, I kind of get it, but it also kind of sounds a bit complicated for somebody like me. So I sort of reframed that quote into: machine learning lets computers learn from data versus being explicitly told what to do. And this really resonated with me because if you think of what we as engineers kind of do all day, every day, it's to explicitly tell a computer to do something. It's very 1 and 0. ML is more like, hey, computer, here's a vague idea of a problem I want you to solve. Let me know how you interpret future questions I send your way, which is a whole new paradigm. And to use machine learning in practice, you need a model, kind of like the brains of a machine learning runtime. So at its core, an ML model is generally a file that's been trained to recognize patterns in data. Could be images, could be text, could be audio, you name it. But these model files are really only as smart as we train them to be. For instance, if I train a model on cats, using publicly available cat pictures or whatever, would this cat be recognized? It's certainly a cat, like probably a 3-year-old could identify it as a cat, but it has no fur, it's wearing a robe for some reason. So to find success in machine learning, to me, it's all about providing the right instructions or the right blueprint to kind of enable your model to learn appropriately. A lot of it is garbage in, garbage out. So if you put bad knowledge or bad instructions into a model, you're going to get bad results out, which I learned in this project, as you'll see. So for today, let's think of ML as this means of providing some guideposts for a computer to learn from and make its own inferences. And a subset of machine learning is this field of tiny ML. And for those of you who don't know, this is kind of the idea of utilizing small but highly optimized ML models on low-powered devices, microcontrollers, or even smartphones. We'll be doing that today, single board computers as well, with the Raspberry Pi. And this also ties into another really important concept you've likely heard about, that being edge computing. Edge computing, of course, is a super important concept in this realm. I'm sure many of you are well in touch with edge computing, but with edge computing, you are physically, of course, moving computation closer to the source of data. Think smart meters, smart street lights, rain gauges in the field for irrigation. It's, of course, more secure to process data on the devices versus transferring everything back and forth from the cloud. And then you obviously, along with that, have reduced bandwidth requirements when you're making these calculations and inferences on a device versus sending all that data to the cloud for processing. And to throw yet another machine learning term at you, we get to TensorFlow Lite. TensorFlow Lite is a platform from Google that enables on-device machine learning. Again, you can create inferences on extremely low-power devices like microcontrollers and smartphones and such. There's TF Lite SDKs available that work with a variety of languages and run on pretty much anything you can imagine. Finally, to build on this story and to make the usage of TensorFlow Lite even easier, we have services like Edge Impulse. Now, with Edge Impulse's mostly web-based tooling, you can actually create, train, and test your ML models all in a browser using the really engaging tool set. This is what I use for this the Speed Trap project, and I'll show a little demo of that in a bit. And as one last kind of explanatory slide about what we're going to be talking about today from the ML perspective of the project, we are talking about image-based machine learning because we're capturing images of vehicles. And at a high level, there's 3 types of image-based ML problems to be solved. The first is image classification. We're answering a single question. Is this a dog? Right? What single object does this image represent? The next is object detection. How many objects are in this image? What are the objects in this image? This is used with Edge Impulse in this project today. The last is image segmentation. So not only what are the objects in this image, but where are they precisely in the image? Now, each level as you step up here requires more horsepower from your microcontroller, as you might imagine. So when you talk about image processing, it's really important to have some pretty beefy hardware behind it. So I started to feel a little more comfortable about the ML part of the project. And next, per the title of the talk, of course, you know, I did decide on the Raspberry Pi 4 Model B. If you're familiar with the Raspberry Pi ecosystem, you'll know the 4 is the most powerful model available right now. It does run Raspberry Pi OS, which is based on Debian, a flavor of Linux, but it is kind of a power hog. So using it in off-grid settings can be kind of tricky. Now, I effectively kind of sort of solved that problem by powering my Pi with a 30,000 milliamp USB power bank. This one is actually so big, it's not legal to fly with it. However, due to some additional hardware I needed to add to the project, as you'll see in a bit, I ran into some occasional low voltage warnings on the Pi, which kind of screwed with my project a little bit. So at the risk of taking a tiny detour here, I did want to talk briefly about the feasibility of using a Pi in a remote setting. You know, turning a Pi into an edge computing device can be incredibly useful when you're doing a lot of processing, but it comes at quite a cost. I did write up a couple of tutorials that I posted on Hackster that cover solar powered crypto mining, which is as ridiculous as it sounds, and also optimizing a Pi for off-grid power consumption. If you want to take a look at those, you can find it on my Hackster page here. But I did have to use some of the latter configurations in this project in order to have it be successful in a remote setting. Now, next up, I knew I needed some kind of a module to measure speed, and I found a really fantastic, albeit kind of pricey piece of hardware from OmniPreSense. It is a Doppler radar sensor that can pretty accurately measure object speeds in about they claim in about a 1 to 100 meter range, which seemed to be pretty accurate for me. Also communicates over serial, which is ideal for a Pi. Bit of a power hog when active though, so this is why I had to utilize those other power optimizations I just mentioned. And since I'd be out of range of Wi-Fi, of course, self-serving, I kind of went with the Blues wireless note card to add low power cellular connectivity. To use the note card with a Pi, I added it to a Pi hat we affectionately call a Notecarrier Pi. This literally plugs into that 40-pin connector on top of every Raspberry Pi. And of course, due to the low power consumption, and it was a great option power-wise because, like I mentioned, when idle, it sips about 8 microamps. So it barely even registers on the Pi. And zooming in on the note card really quickly, I have one in front of me here, which you probably can barely maybe see. It's a very tiny little system on module here. It is a low power cellular and GPS module, 30 by 35 millimeters, has an M2 edge connector for embedding in your project. As I mentioned earlier, the API, so the way you interact with the note card is all JSON. So really gone are the days of these archaic AT commands to manage your cellular modem. We also have SDKs for Python, Go, Arduino, and C as well. There's note card varieties that work globally using NB-IoT, LTE-M, and Cat1 cellular protocols. And again, I don't want to get all salesy here, but it is important to understand kind of our note carriers. And so I did mention that note carrier Pi hat. Note carriers really act as a bridge between your microcontroller or single board computer and the note card. The idea here is to make it easier to use your note card when you're prototyping, or even when you're ready to embed in a more permanent solution. So there are dev boards that allow you to snap in a note card and connect it to really any solution you can dream up. So We have the Notecarrier AF, which includes a feather compatible socket. The A includes headers that you let you hook it up in any way to any microcontroller you want. The B is a small form factor Notecarrier. And the Pi, of course, is what we're going to use today. It's a Pi hat for working with any Pi compatible single board computer. Okay, so I have a cellular module, can relay data from my Pi, but where does that data go? Well, again, we have this service called Notehub that will route data to any cloud. This could be AWS, Azure, Google Cloud, or really any IoT SaaS platform. So really any RESTful endpoint can receive data from Notehub. I kept this pretty simple and I relayed data from Notehub to one of my favorite cloud-based dashboard tools out there, that being UbiDots. And again, to totally clarify here, Notehub is a very thin layer that receives data from Notecard and in turn routes it to your cloud app of choice. Within Notehub, you can manage fleets of devices, you can update firmware for your microcontroller and Notecard, and really, Notehub is all about securely transmitting data both from the Notecard and to your cloud, all off the public internet through private VPN tunnels. And finally, yes, I did use Edge Impulse to create a new object detection model from scratch. And as we'll see in a sec, I ended up supplying my model, I think it was, it's on here somewhere, maybe not this slide, but 200 images, I think. If I were building a production ready version of this, I'd probably 10x that number. My model, even with about 200 or so images, did end up with a accuracy of about 87%, as you can see here, which isn't too bad, all things considered, but we'll come back to this. So at this point in the process, I have a rough idea of what this project's going to become, right? We're going to use an ML model to identify vehicles. I want to be clear, it's not identifying individual vehicles. So we're not registering license plates or makes, models, colors, anything like that. It's just, is it a vehicle or is it not a vehicle? We're of course using a Doppler radar sensor. Again, not cheap. I think it was about 250 bucks, but it did really quickly and really accurately sense the speed of objects in front of it. We're of course using a cellular note card to relay data and a cloud-based dashboard to pretty it all up and make sense of the data that I'm sending. And yes, to focus in on this Edge Impulse thing, I did create a model from scratch. To do that, I sat down for about a half hour, an hour with my phone and took pictures of every car that drove by on this street where I knew I wanted to deploy this solution. And yes, even a cop at one point, which I thought was awesome. And you'll notice the box that is drawn around the image there. This is from Edge Impulse. So part of the process of creating your own Edge Impulse object detection model is to classify what and where objects are in both your training and your testing images. And you'll see this slick UI that they use. So what I want to do is take you on a really quick kind of high level journey through this process of creating an object detection model with Edge Impulse. I really can't say enough about this team and their services, but I'll try to do them a little bit of justice here. For simplicity's sake, I am glossing over some of the steps. It did take me longer than just a couple minutes, as you can probably guess. So step one-ish is to acquire data. Ideally what you want, and I learned this lesson the hard way, you want in-context images of what you're trying to identify. So for me, this meant taking pictures of vehicles that were literally on the same road I was going to be monitoring. I ended up again with about 200 or so images, a decent start. If I could do this, or if and when I do this over, what I probably should have done is actually taken those images from the Pi, because then I'd match resolution and image quality as well, because my smartphone resolution, the images of my pictures captured on the smartphone is obviously much higher than what's captured on the Pi. And the most tedious part of this process is to then manually classify each image and use a bounding box to select what I actually want to identify. It's kind of slow no matter what, but Edge Impulse does make it as easy as they can by providing this cool web-based tooling, of course. But the even cooler thing is over time, it starts to learn what you're trying to sample and will attempt to predict where the box should be drawn as time goes on. So with my data set relatively set, I was ready to create my model or create an impulse in Edge Impulse speak. So this meant adding an image processing block, adding an object detection learning block, and finally classifying multiple features. Now I did skip a step here where I included images of bikes and motorcycles to start to kind of differentiate between some objects that may also be on the road. Again, if I could do this over, I would have added more, non-vehicle images in here as well to improve the model. I did take some shortcuts here, as you can tell, as I was really just focused on cars. And drilling down into it, here's an example of one image's raw data. You can see an example of what I was dealing with on the Pi. So the car, really tiny there, but you can see the car is accurately identified in that bounding box. And yada, 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 time goes on. We trained the model based on the data and the configuration parameters I had supplied. Edge Impulse allows you to dive really deep into some crazy config parameters that I do not even remotely understand, but I kind of stuck to the defaults. And with my model trained, again, I had set aside a small segment of the images to test my model. And after testing my initial accuracy of identifying cars versus bikes versus unknown images, for example, came out to be about 87% accurate. Not amazing, but pretty decent enough to, put a little demo together. Again, in hindsight, should add a lot more images, but for now, we can just pretend that the model is perfect. And at this point in the process, I'm ready to build this model so I can actually use it somewhere. Again, there's a web-based UI to build a model, but I found it even easier to use the Edge Impulse CLI on the Pi directly to generate and download the model file itself. So you end up with a .eim file that your Python code can consume. Really pretty slick. So taking a bit of a breather here, I've got all these puzzle pieces of hardware and services together. What can I build? What can I code to complete this project? So we can take a look at the high level workflow here. You probably have a decent idea of where this is going, but just wanted to level set a little bit. Since I chose a Raspberry Pi, I'm of course going to use a Pi camera module to take video. Now I'm sampling the video at 10 frames per second, which is a pretty decent speed at which to generate really fast inferences with Edge Impulse. And we'll see this in action in a little bit. Of course, then step 2 is to run each frame of video through the Edge Impulse runtime. So you're generating these inferences on these video frames using that Edge Impulse runtime. If a match is made, so if we think that we're looking at a car, we quickly then sample the speed using that Doppler radar sensor. Once we have that data collected, well, it's time to pass it on to the cloud in real time via notehub.io. Notehub is going to process and optimize that data payload and pass it on to my cloud dashboard at Ubidots for a friendly display. And this all from beginning to end happens in a matter of seconds, or actually really less even. So my initial kind of cobbled together ridiculous solution looked like this. And this is what's hanging on my wall over here. Again, this is using a Raspberry Pi and a Pi camera module in the upper left. The radar sensors dangling down there. In the upper right is a 7-segment display just there. Because I've noticed a problem I have in the field is if I don't get any literal feedback from my project, I kind of question whether or not it's actually working. So what I would do is I would send the actively detected radar sensed speeds to that 7-segment display just to make sure something was actually happening. So now I want to take a few minutes and look at the code I had to write. It wasn't nearly as bad as I thought it was going to be honest. I did choose to use Python. Why? Well, I mean, it's pretty easy, incredibly well supported by all the hardware and services I chose to use. So first we can take a look at the speed module. And I'll be honest, ahead of time, most of this, I was able to just copy and paste from the Omni Presense folks, as this module, the speed module's only function is to provide me the speed of an object it sees in front of it. And I'm not going to read through every line of code, but I did want to kind of copy and paste in here some really key parts and kind of introduce you to the concepts and cover the important bits here. So with the radar module, we're initializing serial access, since to me that's the easiest way to access it with the Pi. Frankly, you just plug it in via USB and you're good to go. You might have to change that port up though, depending on your Pi configuration. Next up, you're setting some constants for the module. Some of these are pretty intuitive, like the units of measurement. Some are kind of odd looking commands that I had to look up one at a time. One of the more important ones to call out is the overlook buffer command. I was initially running into a lot of buffer overrun problems, and I wanted to call out the OmniPreSense folks because they were super responsive in helping me debug that and provide a solution. Finally, we get to the all-important OPS get speed method. Basically what this does is it runs continuously sampling for an object that's in motion in front of the sensor. And if it finds something, it returns a float with the speed. Super simple. Now I got really creative with the one other Python script I had to write called main.py. What are the steps in main.py? Well, I have to initialize some variables for edge impulse in the 7-segment display. So for edge impulse, all I'm doing is supplying the path to that model.eim, so the model file I created. I then have to initialize the note card to communicate over I²C. I associate in the second block there the note card with a project on Notehub. And what's cool about the note card is there's a lot of different ways you can configure cellular access here. I chose to keep it in periodic mode, which means to only turn on that cellular modem periodically to save on battery. And finally, and this part's kind of optional in the third section here, but I also enabled the GPS module to sample location, but only sample it when device is moved. So GPS, if you're not aware, it's a very expensive operation in terms of time to acquire satellites and power as well. So it's best to only grab location when you really need it. Now, the meat of the application is in this for loop that is populated by the edge impulse runner or the edge impulse runtime. Effectively, what we're doing here is continually running video frames through the runtime and checking the provided result array for a bounding boxes key. If that key exists, we know that something was identified from that video frame. And continuing on in this loop, if that something is identified as a car, because remember I classified objects as cars or bikes in my model. So if it's identified as a car and the runtime is at least 60% confident in the result, what I want to do next is quickly grab the speed the vehicle is traveling. I also want to grab the speed limit that I set using some cloud-based environment variables with Notehub, and then grabbing the most recently acquired GPS location, which I just defaulted to my location just for ease of use. Finally, to round this out, I set a Boolean to check whether or not they're speeding, which I considered to be greater than or equal to 5 miles per hour over the set speed limit. And then I send what is called a note or an event over cellular to Notehub. You'll notice this note is all JSON, that's it. So there's no other networking ceremony required. So this command is really pretty much all you need to send data over cellular to the cloud. And really, when it was all said and done, the total lines of code here for main.py was about 166, as it says. The speed module is like 80, so we're talking roughly 250-ish lines of Python for the whole app. So I've got data actively being pumped out of my device to the cloud. And where does that data first go? Well, we know it goes to our cloud service Notehub. Within Notehub, you can identify devices that are connected to a selected project. This, of course, is the speed trap project. When we start browsing for events, we can see all of the speed-related events captured. I did want to single out the body column here, as these map exactly to the payload that I sent from the Python app. So everything about that speeding event, or that whatever we want to call it, is in here. And zooming in a little bit, we can see that here's the payload content. I know it's kind of small, but the payload I sent is there. But we also see additional metadata associated with this note. So we can choose to use that data or ignore it. So there's some location-based data in here, info about the cell tower used, timestamps, all sorts of IDs, and so on. But really, Notehub is not meant to be the final resting point of our data. We want you to route your data to your own cloud. To do that, we use a concept called routes in Notehub. So with a route, I can literally process and send data to any RESTful endpoint. In this case, again, I'm using Ubidots. I pass in an auth token I received from Ubidots. I pass in the endpoint URL, again, provided by Ubidots. I tell this route which data I want to send. I obviously don't want to send every single event that comes from this system, just the ones that I've identified as speeding events. And finally, I think this is probably the most underrated feature of what we provide. I can transform data on the fly in Notehub using JSONata. So what I'm doing here in this JSONata expression is I'm filtering out all the data I don't care about. and even doing some simple calculations before that data is then sent on to UbiDots. So we get to the point where here's my actual deployment. Now on this particular road, the speed limit is set at about 30, and people, it was obvious to me going into this, but people routinely go considerably faster. But my assembly here was a little cleaner than my test implementation, but still not exactly ready to be commercialized. And the results, well, this is the final UbiDots dashboard. When I calculated that speeding event is going, like I said, greater than 5 miles per hour over the speed limit, I found that about half the cars were technically speeding, with the fastest clocking in at about 54 miles an hour. Super fun project. You can read more about this project in particular on my Hackster page as well. And I really can't continue talking about the project without acknowledging some of the awesome comments I've received about it along the way. I love I don't need a Hackster guide to build a snitch, or so he built a Karen. Like, truth be told, yes, it is a bit of a Karen-esque kind of project. I'll give him some credit here, but I can't emphasize enough that this project never did and never would accumulate any private data. So again, no license plate data, no pictures are saved, not tracking anything like make, model, color of a car. It's really just aggregated sensor data. And with the time left, I wanted to see if I could actually do a live demo of this project. Now, granted, if you look behind me, you can probably tell I'm in a basement office, not outside. So this brings up all sorts of ridiculous issues that we're going to walk through. So let me stop sharing here. And instead, I'm going to switch my camera over to, okay, you should now not see me, but see what's going on beside me. Let me wake up the computer. So what we're seeing on the wall here, and I hope you can still hear me okay. Caroline, give a shout out if the audio fades out. But again,
you're all good right now.
Okay. What I've set up on the wall here is similar to what you saw in my test setup. I've got my Pi camera mounted, I'll say in air quotes, with duct tape to the wall. I've got my Pi here with the Notecarrier Pi hat and the note card. And I've got a Molex antenna here that allows me to get cellular access, even in my basement, which is pretty nice. What you can barely see here, it's probably, or maybe it's just visible. Here's that the Doppler radar sensor. I think it's funny that they chose to use blue and red lights there, if you can maybe see, as an activity monitor. This is just a switch that I use to switch between my Pi and a PC. So it's not part of this project. Now, how am I going to test this out? Well, this is the ridiculous part. Well, one of the ridiculous parts here. I've got a little Matchbox car here. So you can imagine, like, if I trained a model based on real cars, how well is a Matchbox car going to work? Well, we're going to find out. So what I'm going to do, I'm going to just start running this. So I've got on the Pi, which again, you can probably barely see because it's probably all washed out. I've got the Thani Python IDE running in here, and I'm just going to start running this. And I'll kind of talk through this since you won't be able to probably read too much from it. And of course, the first thing we get is an error, which is awesome. So what I'm going to do, usually this means there's an issue with the serial interface. So I just have to unplug that radar module and plug it back in and hope for the best. Let's run that again. Okay, so we're setting some of those configurations on the Doppler radar sensor. Hopefully you can read this, but probably not. What it's saying is it's found 0 bounding boxes. This is coming from the Edge Impulse runtime. And it's showing how long it's taking to process those individual frames of data. And it's averaging under 400 milliseconds. So each frame of data, the Edge Impulse runtime is taking that data, running it through the model in 400 milliseconds, which I think is really awesome, especially for a device like the Pi. Now, what I'm going to do is I'm going to, again, I just laugh at myself. I'm going to take this car and we're going to drive it in front of the sensor. But it gets even more ridiculous because to properly do this, I also need to use my other hand over here and fake out the Doppler radar module to register a speed. So we're going to start doing this, and I'm going to just look like an idiot as I try and get one event to register here. And it usually takes a little while because the car has to be like in perfect alignment to be registered with any reasonable confidence. Can't seem to talk when I'm doing this at the same time. And I'm sure it'll work at some point, right? Let's see. We'll get something here, I promise. Every time I tested this out, I would get something eventually. It might take 30 seconds or so. And if it doesn't work, I'll just show you the data I accumulated earlier today. Oh, but it's fun if it actually works. All right, well, in the interest of time, I might have to call this a failed demo. You can tell I don't want to give up. I'm actually kind of surprised. Oh, well, I'm gonna let that run anyway. And instead, what I'm gonna do is, so let's pretend it actually worked. And let me switch back to my camera here and share my browser window. So let me reload this page. So again, here's notehub.io. We can see our device was registered 2 minutes ago is the last it was seen. And we can browse all of the events accumulated. And we can see when I last tested this about an hour ago, here's this speed.qo note file, we call them. So here's an event that was sent to Notehub. And again, all of the data associated with this event, can kind of look at it more closely. So in this case, I had a 50% confidence rating using the little matchbox car here. Was it speeding? No, it wasn't speeding, because the speed was captured at a whopping 2 miles an hour. And so when I was flailing my arm like this to get the radar sensor to capture something, it captured me moving at 2 miles an hour. So that was all well and good. So, well, I wish it had actually worked, but I'm glad I was able to capture it earlier today to actually see something. So let me head back to, let's see, I can share this. So with that, I mean, that's about all I wanted to show. Like, thanks everyone for attending. If you're looking for any next steps, of course, take a look at dev.blues.io for a variety of developer resources we have to learn more about Blues Wireless and what we're all about. We did want to offer 15% off any starter kit from the Blues store at bit.ly/riot-speed. And of course, if you want to learn more about Edge Impulse, head to edgeimpulse.com. They do so much right. They are such a joy to use. So that's it. Thank you all very much.
Awesome. Thank you so much, Rob. At this time, please feel free to unmute yourself and ask any questions. We'll leave it open for a few minutes.
I know there's one question out there at least.
I know, right? Don't be shy. If you feel more comfortable, you can use the chat box. I'll read it out loud for you. All right, Rob, here's one from Jim. Rob, could you please intro the SWAN, SWAN, and if it could fit in this app?
Yeah, that's a great question. So just last week or the week before, we introduced our own microcontroller. It's called the SWAN. I actually have it right back here. It's almost like this is a planted question. So here is the SWAN. It is the most extensible feather compatible microcontroller available. So we expose, like, I mean, it's ridiculous, using the castellated edges, which you can barely see here. It's something like 55 GPIO are exposed here. It's using a pretty powerful but low power processor from STM as well. And could it be used in this project? Absolutely. I mean, we actually worked with Edge Impulse to provide day one support for this microcontroller. So it's certainly possible to use, and in fact, in many ways would be better than a Pi for all the obvious power reasons.
Awesome. Thanks for showing that. Thanks for the question, Jim. Leave it open for another minute. Thanks for providing the discount off the note card, Rob. That's awesome.
Yeah, absolutely.
Everyone's just saying, very great presentation. Thanks for the presentation.
Cool.
All right. Well, if anyone thinks of any questions afterwards, you can always feel free. I can connect you. And then Rob has his Twitter down there. A question did just come in from Paul. What system resources were used, Rob?
Can you clarify the question?
CPU utilization, memory, etc.
You know, I never actually looked at that, but I probably should have. One of the steps I had to take when I was kind of optimizing the power consumption on the Pi was to, as I would classify it, throttle down the CPU a bit. And along with that was turning off like any LEDs that were on the Pi, which I mean, we're talking about like tiny bits of energy consumption here, but yeah, so I don't have any hard metrics here in terms of what the cost was. But again, I mean, I'd love to rebuild this with a more standard microcontroller to see how it would compare with a Pi.
And then Paul also wanted to know, do you know the frames per second?
So the frames per second from the video was 10, and that was all about finding the happy medium for grabbing a frame and doing that processing with the edge impulse runtime. I wanted to make sure that I wasn't gonna, overrun the runtime with a bunch of frames. So that took a little bit of, give and take here and there, because ideally you want to process as many frames as possible, but 10 I found was pretty good.
Awesome. All right. Question here from Christina Ubadate. Christina, Rob, what kind of IoT solutions are growing faster within the Blues ecosystem? And also she said, thanks for the great presentation. I love your projects.
Yeah, it's a good question. So I would say right now, like asset tracking is pretty popular with us. Now, asset tracking is pretty commoditized in the market, but our angle is to kind of put together a really low cost tracker. In fact, again, I don't mean to be salesy, but if you just take our note card with a Notecarrier, you don't need a host microcontroller to have a asset tracker work. So that's been one thing. Tank monitoring is really popular. I mean, really anybody who is looking for any kind of off the grid monitoring, even remote control is popular. Like if you don't need highly synchronous remote control, if you're comfortable sending a command over cellular and knowing that it'll get there within a few minutes, if you're comfortable with that, that's really popular as well. Anything, it's pretty amazing what you can do with cellular. And of course, we're not anti-Wi-Fi or LoRa. In fact, we're looking really closely at those markets as well. But it's been cool to hear about people talking about how cellular connect. I mean, not only is it more secure, but it connect as a backhaul for like Wi-Fi, for instance, like if your power's cut or if there's any kind of security incident, like you can rely on cellular versus any kind of local networking. So anyway, it's kind of a long-winded response to, there's a bunch of different things going on. Yeah.
That's awesome. Thanks, Rob. Thanks for the question, Christina. Awesome. All right. Well, thanks again, Rob. Thank you everyone for being with us. Please reach out to Rob directly with any questions, and please be sure to utilize his special 15% off discount. Thanks, y'all. Take care of yourselves. Bye.
Hi, thanks everyone.